All right, everyone. We had some questions for homework last night on page 112, questions number 1 to 8 or 1 to 9. We had some requests to go over questions 3, 5, 6, 7, and 8. So let's take a look at number 3 right now. It says, for a projectile, there's a location on its trajectory where the acceleration and velocity vectors are perpendicular. Explain. What does perpendicular mean? It's funny, sometimes we just read a question and we struggle to get an answer, but we struggle to get an answer because we don't really know what one of the words in the question means. What's perpendicular mean, right? Right, 90-degree angle, right? So we got an acceleration vector that's 90 degrees from a velocity vector. Where would that be? As the object is undergoing projectile motion, a parabola, where is the velocity one way and the acceleration 90 degrees to that? Let me give you a hint with a question, with another question. Which way is the acceleration, when we're talking about projectile motion, always directed? The acceleration is always in the same direction. Which way is that? Jonathan? Downwards. So if the acceleration is downward and the velocity has to be perpendicular to that, then the velocity has to be horizontal, right? At which point along this path here is the acceleration downward? Well, everywhere. At which point is the velocity all horizontal and none vertical? At what point do we have no vertical velocity? At the top, right? What happens when it gets to the top? Well, vertically, horizontally, it goes at the same speed. Vertically, it slows down, stops. So at the top of the circle, you've got only horizontal velocity. And of course, you've still got vertical acceleration because you always have vertical acceleration there. So at the top of the arc, at the top of the parabola, the acceleration would be downward, the velocity would be horizontal. They're going to be perpendicular to each other. For a projectile, is there a location in which its trajectory, on its trajectory, where the acceleration and velocity are parallel to each other? In other words, is there a place where the velocity is straight down? There's a quick and simple answer to that question. The answer is no. Why not? What did we just say about the horizontal velocity? It doesn't change. The vertical velocity does. The vertical velocity decreases as it goes up and increases as it goes down. But if the horizontal velocity doesn't change, there can never be a time when we have a velocity downwards. Think about that. If you always have a horizontal velocity like this, then the vertical component of the velocity can never be the entire velocity because you've always got that horizontal. Does that make sense? So the answer to the first question, yes. Yes, there is a place at the top of the arc. The answer to the second question, no, because you always have a horizontal velocity. Therefore, you can never have entirely a vertical velocity, and you need a vertical velocity for it to be parallel to the acceleration. Next question that we had requested here, number 5. Says participants in a road race take water from a refreshment station, throw their empty cups away farther down the course. If the runner has a forward speed of 6.20 meters per second, how far in advance of a garbage pail should he release his water cup if the vertical distance between the lid of the garbage can and the runner's point of release is 0.50 meters? You know what? This isn't a hard question. It's the wording of this question that's tough. If you can't get past the wording, then it's a really tough question. We've got a garbage pail right here. Let's draw it over here. There's my garbage pail right there. We got our runner. He's not really running. He's more standing there. Look at that. Now he's running. We got a runner, and he's got a water cup. He's moving, and the water cup, by the way, the little water cup is moving at 6.20 meters per second horizontally. Now, we want that water cup to land in the pail. The lid of the garbage can, it says, is 0.5 meters below the pail, or below the cup. We want to find out, what do we want to find out? We want to find out this distance right here. This is a regular projectile motion question. It is, right? We want to find out how far this cup goes when it's released from a height of 0.5 meters at a speed horizontally of 6.20 meters per second. So, no funny angles to worry about here. Let's just break it up into that x and y components. We always know to do v is equal to delta d over t. No exceptions to that, right? You get your test tomorrow. I promise you there will be 2 projectile motion questions on that test. One where it's launched horizontally like this. One where it's launched at an angle at 30 degrees or 50 degrees or whatever the case may be. In both cases, you need to start like this. V equals delta d over delta t. And for the y component, d is equal to vit plus 1 half at squared. That will get you right there. Even if you know nothing else, that will get you part value for both of those questions. Right now, if you do this, you are guaranteed tomorrow of not getting a 0 on that test, which I hope you weren't going to get a 0 anyways, but just in case, now you're not. Okay, let's fill in some blanks. Okay, let's plug in some numbers. It's what we do, right? The velocity, horizontal velocity, 6.20 meters per second. That's how fast the runner's running. That's how fast the cup he's holding is moving. How far does it go? We don't know. That's what we're trying to find. How long is it in the air for? We don't know. Now, the y displacement is negative 0.5 because the cup ends up 0.5 meters below where it started. Vi for the y component is 0 because it's launched horizontally. The runner isn't running up a hill. Okay, the runner is running horizontally, therefore the cup will be released horizontally at the speed the runner is running at. Then we're going to solve for t. Does anybody have a value for that? For t? Merrick 0.309. Anybody else agree with that? Yes? All right, so there's my time, which I'm going to turn around and plug back into here. 0.309 times 6.2. That's going to be about 1 point, I'm going to say about 1.9. 1.88, 1.9. What is it? Oh, 3.319? Okay, so what's the displacement there? 1.98. And we're going to round that to 2 digits, right? So it's going to be 2.0 meters, right? Next time you're running a 5K race, Sheep River race, September. Okay, they give you those cups of water. Okay, you throw it in there. Make sure you bring your calculator with you so that given your average speed, you can determine how far in advance you need to be at the garbage can so you don't litter. Okay, got that? Be a responsible runner, an earth-friendly runner. Okay? Everybody got that? 2 meters? Good? All right, let's take a look at number 6 then, please. This one says a baseball was thrown with a velocity of 27 meters per second at 35 degrees. What are the components of the ball's initial velocity? So in other words, what's the x component, what's the y component? All we're asked for in the beginning is, hey, we don't like the funny angle. Break it down into its x and y. Just go off to the side, do your thing. You've got the answer to the first part of the question. This is x, this is y. Cosine 35 degrees. And we're going to say sine 35 degrees is equal to y over 27. What's 27 cos 35? There's the horizontal component, and the vertical component is 27 sine 35. Zach, you got that one? .48 meters per second. Good, thank you. Done. First part of it's done. Now, second part of it says how high and how far will it travel? This is what we're usually asked for, right? It's how far is it going to go? What's its maximum height? So let's break it into our x and y components again, like we always do. You're going to do this twice tomorrow. Might even be question 1 and 2. I'm not sure. Can't remember. Let's not worry about what I'm looking for right now. Let's plug our numbers in and see what happens here. The horizontal velocity is 22.11. We figured that out a minute ago. Zach gave us that number. The horizontal displacement, we don't know. In fact, that's what we're trying to find, right? How far will it go? The horizontal displacement, don't know the time either. The vertical displacement is 0. Initial vertical velocity is 15.48. T's cancel. We can divide every term by t. That's really what we're doing here, right? Dividing every term by t. I'm just not showing all that work this time. If you need me to show it, just let me know and I will. Half of neg 9.81 is neg 4.905. That's going to work out to be about a third, 12.3 seconds roughly. Thank you. 3.157, and that would be seconds. Plug it in here. And now multiply 3.157 by 22. It's going to give me about, I don't know, 77 meters, 67 meters, 69 meters. It would be 2 digits, because if you go back to your original data, 3 digits, this is 2 digits, our weakest piece of data. Sorry? 69.8, but, so it'll be 70 meters then, right? Still 2 digits, but rounded wrong there. Our weakest piece of data is our angle there, and that's 2 digits, so our final answer is going to be 2 digits. That's how far it's going to go. Right? We've done that question a million times. Now, something that's a little bit more challenging, just because we haven't done it as often, how high is it going to go? Well, here, we got a couple of options here, actually. A couple of options. What I would probably do is say, for the y component, vf squared is equal to vi squared plus 2ad. That's what usually you guys are doing. When I asked you what to do, I think it might have been Hugh, maybe, who told me what to do. I'm not sure about that. A couple of days ago. Want to find maximum height? Vf squared is equal to vi squared plus 2ad. But Vf is 0 when we're analyzing only the trip up. Vf is 0. Vi is the y component, 15.48 squared plus 2 times neg 9.81 times displacement. So we take this over by subtracting, and then we take this over by dividing, and then we solve for delta D. Done. Does anybody know what the other option would be here? How else could we have solved for the max height there? By the way, the max height would be, what does it work out to be, about 11-ish? What else do you want to try there, Ben? Good. You could divide time by 2, so 1.6 seconds almost. Okay. And then say d is equal to vit plus 1/2 at squared and solve for d. Okay. We have the displacement over the entire trip. It's 0. But the displacement over half the trip wouldn't be 0. It would be whatever the maximum height works out to be. So either way is fine. I wouldn't say that one is necessarily even harder than the other unless you haven't already solved for time. If you haven't solved for time, then this is the easier way. If you have already solved for time, then they're both about the same. Should get the same answer either way, though. All right? And finally, we had questions 7 and 8 here. 7 says a football was thrown. Oh, this is a tricky one, too. Both 7 and 8 are tricky. A football was thrown to a moving receiver. The football leaves the quarterback's hands 1.75 meters above the ground with a velocity of 17 meters per second. The receiver starts 12 meters away. What constant velocity must she have to get the ball at the instant it is 1.75 meters above the ground. In other words, you're throwing it from 1.75 meters above the ground at an angle of 25 degrees. It's being caught when it's 1.75 meters above the ground. So it doesn't matter whether it's 10 meters above the ground or 1.75 meters above the ground. If it lands at the same height that it started at, or is caught, I should say, at the same height that it started at, then the vertical displacement would be 0. Okay, we got a funny angle here. Marie's been absent for a while because she's been recovering from her concussion here. The rest of you in this class are going to know that when we see this funny angle, we should think 5 words. Marie, don't forget these 5 words, okay? What are they? Elizabeth? I don't like funny angles. You look it straight in the eye and say, I don't like you, funny angle. Let's get rid of you. So we do that. We go over here. We get 25 degrees. We got an X, we got a Y, and we got 17. What does X work out to be there, guys? Yep, Michael. 15.4. If you need me to show that work, guys, I will. We've done that a lot of times, so I'm thinking you're okay with that, but if you're not, just let me know. The Y component is, Michael, do you have that one? Jonathan? Sorry? 7.2. Okay, we can replace this if we want. We can redraw that if we want to with 15.4 and a 7.2. And now when we go to do our X's and Y's, you notice that right now we're solving this like any other problem. Although this was kind of worded in a little bit of a confusing way. There's a receiver that starts 12 meters away. The receiver has to run to catch it. It seems to be a bit confusing, but do you know how, just notice how when we're solving this question, we're not worrying about that. We're not worrying about the confusing part. There's a part of this question that's exactly the same as every other question we've done, and that's what we're worrying about right now. Once we finish that part, then we'll worry about the confusing part. Here's what I'm saying. You get this question on a test, solve the easy part, get yourself a 3 out of 5, get yourself a 4 out of 5. And if you have trouble with the end of it, then you've just missed 1 point or 2 points instead of 5 points. Don't get bogged down in the beginning with, oh my goodness, this, I don't know what, we haven't seen one like this. We haven't seen one with a receiver. What do? Do the same thing you always do. And then worry about the receiver at the end. That's what we're doing right now. We've got a horizontal velocity of 15.4 and a displacement, we don't know. Okay. It is not 12 meters. Right? It's not 12 meters. That's how far the receiver is away. That's not how far the ball goes. Hey, it'd be great if the receiver was in the exact right place and the receiver didn't have to run to catch the ball. That doesn't happen. It doesn't say it happens here. So we don't know that the displacement is 12 meters. We're going to have to try to find that number. We know the vertical displacement is 0 because it lands at the same height it started. The initial vertical velocity is 7.2. Cross off a t. At a half of negative 9.81 is negative 4.905. What is that? 7.2 divided by 4.905. I'm going to say it's about 1.4-ish. What is it exactly, Adam? 1.46 seconds, thank you. Which will turn around and plug into here. What's 15.4 times 1.46? I don't know what that number is right now. All I know is it's not our answer. It's not what we're looking for, but that's okay. It's something. What do you get there, Jonathan? 22.59 meters. Okay, good. What have we just found? Not what we're looking for. We're looking for velocity. But what have we just found? Michael? I'm sorry? Right, the distance the ball travels. Now, Sam, what am I going to do with that? That's not what I wanted to find. I wanted to find out how fast the receiver had to run to catch the ball. So what am I going to do with the distance the ball went? Good. So if the ball goes this far, 22.59 meters, and the receiver starts 12 meters away, then that means the receiver has to run 10.59 meters, right? And we know the receiver has to run 10.59 meters in a time of 1.46 seconds, right? That's how long the ball's in the air. What's that equal? Yep. 7.25 meters per second, I should say, right? Thank you. All right, let's take a look at number 8 now. Last question. This is, I think this is a tough one, actually. If you had an opportunity to do the entire worksheet that I gave you, beyond what I assigned on that worksheet, 1 to 3, if you did question number 4, which wasn't assigned, then you would have found that question was a lot like this one. It's a challenge, for sure. In fact, it's more challenging than what you will see on your unit test. It's mental exercise, though, right? It's like in basketball when you practice harder than you have to play. Because sometimes we do that, right? In basketball or hockey or baseball, we work harder in practice than we know the game's going to be so that we're stronger come game time. That's what we're doing right now. We're going to practice harder in this question than we have to play tomorrow in the game, tomorrow on the test. Because at the 2004 Olympic Games in Athens, Dwight Phillips won the gold medal in men's long jump with a jump of 8.59 meters, which is a big jump. That is almost all the way across this room. So he's jumping from that wall probably over to about a little bit past Phil. That's a long jump. That's why they call it long jump, because it's a long jump. He's jumping at 23 degrees, but we don't know how fast. Now, hey, it's a projectile motion problem. We know that, right? So we all have a place to start. The place we usually start is actually to say, look, I don't like funny angles, so let's get rid of the funny angle. The problem is we can't truly get rid of this funny angle without knowing what the hypotenuse is here. I'm going to do something that maybe is going to come in useful later on. Maybe it's not. I'm going to do it anyways, just in case. I'm going to take that 23-degree angle over here. Don't know what the hypotenuse is. No, this is x. No, this is y. I'm going to call this v, just v. I'm going to say cosine 23 degrees is equal to adjacent over hypotenuse, or the x component is v cosine 23 degrees. The y component would be sine 23 degrees, right? V sine 23 degrees. So if I just knew what v was, then I could find the x and y component. I don't. Maybe what I just did isn't going to be helpful, but it didn't take me that long to do, so we're not going to worry too much about that. All right, now break it into x's and y's. V equals d over t, always. If tomorrow on those 2 projectile motion questions, tomorrow night when I'm marking this test, if anybody starts off with these projectile motion questions with anything other than d over t and vit plus 1/2 et squared, I will rip my hair out. Because we always start the same way. I'm telling you, in those 2 questions, start this way. Don't do anything else. Start this way. I come back Friday morning. You see me Friday morning and there's chunks of my hair gone, then you know it's because some of you didn't start this way on these 2 questions. All right, what's the x component of the velocity? Well, we don't really know, but we do know that it's the hypotenuse, v, times cosine 23. So let's replace that right there. We know the horizontal displacement is 8.59 meters, and the time, we don't know. The vertical displacement is 0. The vertical velocity, we don't know its velocity, but we know it's the hypotenuse times sine 23. Let's simplify this a little bit. Somebody figure out what cosine 23 is, please. 0.93? 0.92, thank you. So 0.92 V equals 8.59 T. Over here, let's figure out what sine 23 is. Yep. That should be 0.39 V, right? Forgot the V there. Okay. I get two unknowns, V and T. The good news is I get two equations. Now, I think personally the easiest way to solve this is to solve for one of the variables in both equations. Solve for either V or T. We could say T is equal to 8.59 over 0.92 V. And over here we could say T is equal to, what would it be? 0.39 V over 4.905. Right? This goes to the other side by adding. And we divide by 4.905 to get T by itself. This T is the same as this T, so let's make 8.59 over 0.92 V equal to 0.39 V over 4.905. Oh, look at that. One equation, one unknown. Mathematically, this has been pretty tricky, right? I'm not going to try to gloss over that. It's a tough question. But look at where we are here now. Let's take this up by multiplying and this up by multiplying. What's 8.59 times 4.905? 42.12? Thank you. What's 0.39 times 0.92? 0.3588. V times V is V squared, right? Oh, would you look at that? Now it's even better. Take this down by dividing, and then square root, and what do we end up getting for V there? 10.83 meters per second, which, let's go back to our data to see what our weakest piece of data is. 3 digits, 2 digits. Final answer should be 2 digits. So we're going to say it's 11 meters per second. That's a tough question. Okay, I'm going to ask you a question here. Be careful, though. Listen to the question carefully. The question is not, how many people think they could do this tomorrow if I gave you this on a test? The question is, how many people followed this? How many people did this make sense to as I was working through it? Not how many people got it, how many people could do it themselves tomorrow, how many people followed it? Good. Okay. You know what? You're smarter than you were 20 minutes ago. This makes you smarter. Doesn't matter whether you can get this yourself or not. If you can, hey, that's fantastic. If you can't, that's okay, as long as you followed it, as long as it made sense to you. You're still smarter than you were if it made sense to you. And the questions that you get tomorrow are going to seem easier as a result of that, right? That's why we do a question like that, right? Is because we want the other questions to seem easier. Don't panic if you can't get something like that. Just work hard on it, though. Work hard so that you understand it.